Right now, your Wi-Fi router is basically blasting you with these invisible colors of light that, your eyes just aren't equipped to see.
Yeah, which sounds a bit like science fiction, honestly.
It really does, but it's just the baseline reality of the physical world. I mean, the warmth coming through your window, the literal sound of my voice reaching your ears right now, the data streaming to your device you are sitting, completely submerged in this massive, chaotic symphony of invisible forces.
And, well, because we don't physically see those forces,
Mm,
we rarely stop to appreciate the mechanics of them. We just kind of experience the end result.
right.
We get a lit room or a downloaded file or a heard conversation, and we take that entire delivery mechanism completely for granted.
And that delivery mechanism is exactly what we're decoding today. So, welcome to the deep dive. We're pulling from focused excerpts of a text called Principles of Wave Mechanics and Electromagnetic Theory.
It's a foundational text, really.
Yeah, and I want to be clear right up front. Our mission today isn't to just read you a physics syllabus or run through some dry glossary of terms.
No, definitely not.
We want to deeply analyze the hidden behavior of these waves. We're going to figure out how we measure them, explore how they interact with their environment, and uncover how they ultimately power the everyday instruments you use to navigate your life.
Which is really the most crucial part of this text. The rules governing these waves, they aren't just abstract math confined to a chalkboard somewhere.
Right, they're everywhere.
Exactly. They form the literal foundation of modern human existence. So the goal today is to synthesize these foundational rules so you can actually perceive that invisible scaffolding holding up your daily routine.
So I want to jump straight into the source material because before we can understand how to harness waves in the real world, we first have to understand what a wave actually is fundamentally.
Right, the basics.
Yeah, and the text specifically tasks us with comparing the two most common types we experience. So that's mechanical waves, like sound, and electromagnetic waves, specifically light.
And that distinction is huge. It dictates how these waves are even capable of traveling in the first place.
How so?
Well, we generally know that a mechanical wave, like sound, is essentially a chain reaction. It requires a medium.
Meaning it needs physical stuff to travel through.
Precisely. It needs physical particles to bump into each other to pass the energy along. If there is no matter, there is no sound.
Hence the whole in space no one can hear you scream thing.
Exactly. But electromagnetic waves, like light, are entirely different beasts. They're oscillating electric and magnetic fields that can propel themselves through the absolute nothingness of a vacuum.
Which is why the light from a distant star can reach your eyes through billions of light years of totally empty space.
Yes.
But the text doesn't stop at just comparing their travel mediums, right? It gives us a very specific mandate. It lists 6 critical wave characteristics we have to use to map them out.
Yes. The 6 core metrics: frequency, wavelength period, amplitude, velocity, and energy.
Okay, let's unpack this slowly because throwing 6 physics terms out at once is a really quick way to lose the thread.
It can be a bit dense, yeah.
And we definitely want to avoid treating this like an audio textbook. So let's ground this in something familiar. If I think about a wave like, say, a human heartbeat or a musical rhythm, how does that track?
Oh, that's a highly effective way to conceptualize it.
Okay, so it seems like the period would be the actual time that passes between each individual beat. Is that right?
That is exactly right. The period is simply the time it takes for one complete cycle of the wave to pass a given point.
Okay, so following that logic, frequency would just be your heart rate.
Yes.
Like how many of those beats actually happen in a given minute, or I guess in the case of physics, a given second?
Precisely. In wave mechanics, frequency is measured in hertz, which is really just shorthand for the number of wave cycles per second.
Right.
And what's fascinating to observe is how period and frequency are inversely related.
Meaning they do the opposite of each other.
Exactly. If your heart beats faster, which gives you a higher frequency, the time between those beats, the period inherently has to get shorter. They're just two sides of the same mathematical coin.
Okay, that makes total sense. So continuing that heartbeat analogy, the amplitude would be how strong the pulse actually feels.
Yes, the physical displacement.
Right, because a resting heart rate has a very gentle pulse, but if you just ran a marathon, that pulse is pounding out of your chest. It has high amplitude.
Spot on. Amplitude is the maximum displacement of the wave from its resting position. For a sound wave, amplitude physically dictates how loud the sound is.
So a pounding pulse translates to a loud drum beat.
Exactly. And for a light wave, amplitude relates directly to its intensity or brightness.
Okay, so we have period, frequency, and amplitude mapped out. What about wavelength? If I stick to my runner analogy, is wavelength the distance the runner covers between beats?
Actually, the runner analogy breaks down a little bit there.
Oh, it does.
Yeah, because distance covered is really just an artifact of speed. To visualize wavelength, it's much better to picture actual ocean waves crashing against a pier.
Okay, ocean waves. I can picture that.
The wavelength is the literal physical spatial distance between the crest of one wave and the crest of the wave immediately following it.
Oh, literally the length of the wave.
Right. And if we connect this to the bigger picture, wavelength and frequency are deeply tethered to one another
How so?
because a wave moves at a certain speed, right? So if the frequency goes up, meaning more waves are hitting that pier every second, those waves physically have to get squished closer together. Therefore, the wavelengths get shorter.
Okay, that paints a much clearer picture. The more frequent the waves, the tighter they're packed. That leaves us with the last two characteristics on the sources list, which are velocity and energy.
Big ones.
Right. So how do velocity and energy specifically change the game when we look at light versus sound? Because I know they behave very differently.
This is where the core difference between mechanical and electromagnetic waves becomes incredibly apparent. Let's start with velocity, which is simply the speed at which the wave travels.
Okay.
For an electromagnetic wave, like light, in a vacuum, the velocity is a universal constant. It is the speed of light, which is roughly 300 million meters per second.
The absolute speed limit of the universe.
Exactly. Nothing goes faster.
But for sound, that velocity isn't constant at all, is it?
Not even close.
It depends entirely on what the sound is actually moving through.
That is the crux of it. Sound travels at about 343 meters per second in the air, but it actually travels over 4 times faster through water.
Wait, really?
Yeah, and significantly faster than that through solid steel.
See, that feels so counterintuitive. You'd think moving through solid steel would slow a wave down, not speed it up. I mean, it's a solid wall.
It does feel backward until you remember that sound relies on particles bumping into each other.
Oh, right. The chain reaction.
Exactly. In a dense material like steel, those particles are packed incredibly tightly together. They don't have to travel far at all to hit their neighbor and transfer the wave's energy.
Oh, so the denser the material, the faster the chain reaction occurs because everyone's standing right next to each other.
You got it.
Ah, okay. So light must behave in the exact opposite way then. Because light doesn't need particles to travel, a dense medium like water or glass just, gets in its way.
Exactly. Light actually slows down when it hits a denser medium because the electromagnetic wave begins interacting with the atoms in that material, which bogs down its forward momentum.
Wow.
And that inverse relationship to density perfectly sets up how these waves interact with their environment, which we'll get to in a moment. But we have to touch on the final characteristic first, energy.
Right, energy.
The energy of a wave manifests quite differently for light than it does for sound.
Okay, well, for a mechanical sound wave, I imagine the energy is tied to that physical displacement we talked about earlier, the amplitude.
Yes. A louder sound, a wave with a bigger amplitude, carries more raw physical energy.
So if you pump enough amplitude into a sound wave, it carries enough physical force to literally shatter a glass.
Precisely. But for an electromagnetic light wave, the energy isn't about amplitude, is it?
No, the source mentions it's actually tied to frequency.
And this is one of the foundational pillars bridging classical wave theory into quantum mechanics, honestly. For light, the energy is directly tied to the frequency.
Interesting.
Higher frequency light, like ultraviolet rays or X-rays, carries significantly more energy than lower frequency light, like radio waves.
Oh, so that's why X-rays have the energy to pass right through your tissue.
Exactly, and why UV light has the energy to damage your skin cells and give you a sunburn.
Right, but the radio waves bouncing around your living room right now are completely harmless.
Completely harmless. Their frequency is simply too low to carry any kind of damaging energy.
Okay, so we've successfully isolated the anatomy of a wave. We understand its frequency, its amplitude, velocity, all of that. But if light is cruising along at the universal speed limit, what happens when it violently slams into something dense, like a wall of water or a pane of glass?
That is the big question.
Right, which naturally shifts our focus from simply listing wave characteristics to exploring wave interactions.
Yeah, the two primary interactions, the source mandates we evaluate here are reflection and refraction.
Okay, well, reflection seems straightforward enough. It's just waves bouncing back, right? You look in a mirror, the light wave hits the silver backing, cannot penetrate it, and bounces straight back into your eye.
Yes, and the key mechanic of reflection is that the angle at which the wave hits the boundary surface is exactly equal to the angle at which it bounces off.
So it's a perfect geometric mirror image?
Always.
Yeah.
But refraction is where things start to bend, literally.
Refraction. Okay, explain that one.
Refraction is the bending of a wave as it passes from one medium into another medium of a different density.
Hmm.
We already established that when light travels from air into water, it slows down because the water is denser.
Right.
What we need to understand is that because the wave slows down, it actually changes direction.
Okay, let me stop you there. Because the text states this happens, but it doesn't clearly explain why changing speed causes something to change direction.
It's a common stumbling block.
Like, why wouldn't the light just go straight but slower? Why does it turn?
To picture why it bends, imagine you're pushing a shopping cart across a smooth, paved parking lot,
Oh, okay.
and you push it at an angle toward a patch of thick, dense mud.
All right, I've got the cart moving toward the mud at an angle.
Because you're approaching at an angle, the right front wheel of the cart is going to hit the mud before the left front wheel does.
Right, because of the angle.
Exactly. The mud is dense, so that right wheel immediately slows down. But the left wheel is still on the smooth pavement, so it's still moving at its original, faster speed.
Oh, I see it. Because the left side is moving faster than the right side, the entire shopping cart pivots. It turns into the mud.
That pivot is refraction. Because the wave has width, one side of the wave enters the denser medium and slows down before the other side does, causing the entire wave front to bend.
That is wild.
You observe this all the time, actually. If you put a straight straw into a glass of water, the straw looks completely broken or disconnected at the waterline.
Yes, I've seen that a million times.
The light bouncing off the bottom of the straw is acting just like that shopping cart. It's pivoting as it leaves the dense water and enters the less dense air before hitting your eye.
Okay, that shopping cart analogy completely unlocks the concept.
Yeah.
But here is where the source text makes a very specific demand, and I kind of want to challenge it a bit.
Sure, go for it.
The text says we have to use models to compare reflection and refraction both qualitatively and quantitatively. Now, a qualitative model gives us conceptual understanding, like the broken straw or the shopping cart. Why do we need a quantitative model, too? Like, why do we need the actual rigorous math of Snell's law if we already intuitively grasp that the light bends?
The really valid challenge, why do the complex math if you already grasp the concept?
Yeah, exactly.
The answer lies in the massive chasm between merely observing the world and actually engineering it.
Okay.
A qualitative model tells you what is happening. But a quantitative model, the actual mathematics of Snell's law, which calculates the exact ratio of the wave's speeds in the two mediums, that tells you exactly how much it is bending, down to the fraction of a degree.
It's about precision.
Exactly. Without that mathematical precision, modern technology fundamentally cannot exist.
Wow. Okay, so where is Snell's law actively hiding in my house right now?
Oh, the most immediate example would be prescription eyeglasses or contact lenses. The entire field of optometry is applied Snell's law.
Wait, really?
Yes. If an optometrist only used qualitative models, they would say, well, your vision is blurry, so we need to put a curved piece of glass in front of your eye to bend the light inward.
But knowing it needs to bend doesn't actually help me see.
Exactly. To actually correct your vision, they need the quantitative model. They need to calculate the exact refractive index of the lens material and map the exact curvature required to ensure the light bends at the precise angle necessary to focus perfectly on your specific retina.
Oh, man.
If the math is off by even a tiny fraction of a degree, the light bends too much or too little, and your vision remains completely blurry.
That makes total sense for lenses. But the text implies this goes further into, like, global communication. What about the internet? I know the backbone of global telecommunications is fiber optic cables, which are just tiny strands of glass transmitting data using pulses of light.
Fiber optics are arguably the most brilliant application of Snell's law we have.
But if they're just glass cables and they physically bend around corners under the ocean, why doesn't the light just shoot straight out the side of the curved glass?
That's a great question.
Like, if light hits the edge of the glass, shouldn't it refract into the water?
It absolutely would if it weren't for a phenomenon governed by Snell's law called total internal reflection.
Total internal reflection.
Yes. Engineers use the quantitative mathematics of Snell's law to calculate something called the critical angle.
Hmm.
They design the glass and the angle of the light beam so that the light hits the inside boundary of the cable at such a shallow trajectory that it simply cannot refract out.
Oh, it's like skipping a stone across a pond. If
Yes,
you throw the stone straight down, it plunges into the water. But if you throw it at a really shallow angle, it bounces off the surface.
that is a brilliant analogy. The light beam hits the inside of the fiber optic cable at such a shallow angle that it skips perfectly off the boundary, reflecting back inward.
That's incredible.
It essentially bounces its way down the cable, perfectly contained,
Right.
traveling across entire continents at the speed of light.
And without the math.
Without the exact quantitative mathematics of Snell's law calculating that precise critical angle, the light escapes, the signal is lost into the ocean, and the global internet just goes dark.
So we have literally taken this invisible property, the fact that a wave bends when it changes speed, and we've mathematicalized it to the point where we can trap light in a glass tube to send an email across the planet.
That is exactly what we've done.
That brings us to the final objective of the source text, which is obtaining, evaluating, and communicating information about instruments that transmit and detect waves.
Right.
This is the practical application of the characteristics and interactions we've been breaking down all episode.
And the text explicitly emphasizes that we evaluate instruments used in everyday life. We aren't just looking at massive radio telescopes, we're looking at the tools intertwined with human health and daily convenience.
Right. We just talked about eyeglasses and fiber optics, which manipulate electromagnetic waves. But we also have incredibly sophisticated instruments that manipulate mechanical sound waves.
What do you do?
Ultrasound in medicine immediately comes to mind.
The ultrasound is perhaps the purest example of applied wave mechanics. A machine transmits a high-frequency mechanical sound wave, a frequency far above the limits of human hearing, directly into the body.
Okay.
That sound wave travels through the tissue until it hits a boundary.
Hmm.
That boundary could be the edge of an organ, a change in tissue density, or, a developing baby.
And because it hits a boundary of a different density, it reflects, just like a voice echoing off a canyon wall.
Yes. The instrument's entire function relies on detecting that reflected echo. By knowing the velocity of sound in human tissue and measuring the exact amount of time it took for the echo to return, the machine's computer can calculate exactly how far away that boundary is.
Oh, wow.
It constructs a real-time, quantitative visual map of the inside of the body. It's essentially high-tech echolocation, harnessing frequency, velocity, and reflection to monitor human health.
Radar operates on the exact same principles, doesn't it? Just swapping out mechanical sound waves for electromagnetic waves, bouncing invisible radio waves off an airplane to track its velocity and distance.
The underlying mechanisms are completely universal. Detecting a wave, analyzing its reflection or refraction, measuring its frequency and amplitude, these are the core actions happening inside the technology all around us.
It's everywhere.
Whether it's an antenna picking up your Wi-Fi signal, a microwave vibrating water molecules to heat your coffee, or an ultrasound monitoring a heartbeat, they are all just instruments specifically engineered to interface with this invisible symphony.
Which brings up a great point. The text specifically tasks us to obtain, evaluate, and communicate how these instruments are used. It feels like it's not just about acknowledging that waves exist, it's about acknowledging our active role in harnessing them.
Yes, absolutely.
So, why is the communication part of this mandate so vital? Why does the source insist that we don't just learn it quietly, but communicate it?
It addresses a massive issue regarding modern scientific literacy, honestly.
Okay.
As our technology becomes exponentially more advanced, its operation begins to look increasingly like magic to the average person.
Right, yeah.
If you don't understand that a smartphone is just a specialized instrument transmitting and detecting specific frequencies of electromagnetic waves, you are entirely disconnected from the physical reality of the tool you rely on most.
It just becomes a black box. You press a button and it magically connects you to your bank or your family. You have no idea how.
Exactly. And a society that relies exclusively on black boxes is a vulnerable society. Evaluating and communicating these fundamental principles ensures that we maintain a collective grip on our physical reality.
It demystifies the world.
It does. When you can articulate how an instrument actually works, you transition from being a passive consumer of a magical black box to being an active, informed participant in an engineered reality.
And the more we communicate the mechanics behind the curtain, the more we empower the next generation of engineers who are going to be tasked with building the next set of instruments.
Exactly. Knowledge has limited utility when it's hoarded. It becomes transformative when it's understood, communicated, and applied to to solve actual problems.
Man, this has been an incredibly eye-opening dive into the physics governing our daily routines.
It's a massive topic, but so crucial.
We started by breaking down the 6 basic characteristics of our invisible world, understanding how the period, frequency, amplitude, wavelength, velocity, and energy fundamentally differentiate a mechanical chain reaction like sound from an electromagnetic field like light.
We then explored how those waves physically interact with the obstacles in their environment. We moved from the qualitative observation of a shopping cart pulling into the mud, all the way to the rigorous quantitative mathematics of Snell's law, proving exactly why we need both conceptual understanding and strict mathematical precision to engineer the world.
And finally, we brought those abstract physics concepts directly into our homes and hospitals, connecting the dots to the everyday instruments that define modern life, from the critical angles of fiber optic cables to the echolocation of ultrasound machines.
It all comes down to mapping out those fundamental rules of the universe and then building the tools to harness them.
Which leaves me with one final lingering thought for you to take away today.
All right, what is it?
Well, the source explicitly tasked us to evaluate how everyday instruments transmit and detect waves based on the 6 characteristics we mapped out. But scientific discovery is never a finished project.
Never.
If our current daily life is already completely reliant on harnessing frequency, amplitude, and refraction just as we understand them today, what might happen to our everyday instruments when we discover how to manipulate these exact same wave characteristics in ways our current models haven't even quantified yet?
It is a profound question.
Mm.
I mean, the symphony is currently playing all around us, but we might realistically only be hearing the first few notes.
We're just getting started. Thank you so much for joining us on this deep dive into the invisible forces that shape your world. Until next time, keep looking closer at the reality around you.